Okay. Where's your safety gear?
Come on, Mr. Twain. These goggles make my face and hair all sweaty.
Yeah, these things are so scratched you can hardly see out of them. Besides, we read the directions.
And they said put on your safety gear.
Yeah, but if we're doing everything else, we really don't need...
Put on your safety gear.
Huh?
I said, put on your safety gear.
Who are you?
I'm Ray Seddon, the payload commander of SLS-2 on the Space Shuttle Columbia. And I'm here to tell you that everyone has to follow laboratory rules. You, and astronauts too. It doesn't matter if you're a student in a lab on the ground or an astronaut orbiting the Earth. Everyone in a science lab must follow certain fundamental rules and procedures, including safety. Allow me and the rest of the crew to show you.
T-minus 10, 9, 8. We have a go for main engine start. We have main engine start. 4, 3, 2, 1, 0, and liftoff. Liftoff of the space shuttle, and it has cleared the tower.
It is slow, that's the code.
Make your touchdown.
This is our space lab, a science laboratory in the cargo bay of the orbiter. We can use the space lab to study things like biology and the processing of new materials. On this flight, we're using the lab to study how spaceflight affects the body. The difference between a space lab and laboratories on Earth is microgravity. Microgravity is the result of being in a free-fall orbit around the Earth. Free fall makes things appear to float when they're actually falling. Like me and everything else in our space lab. Even though the crew and I are in this special laboratory, we still have to follow laboratory rules.
Like measuring properly. I'm John Blaha, the commander of this space shuttle mission. Right now, I would like to compare the mass of this ball on Earth with the mass of the ball here on orbit. One way to measure the mass of the ball on the Earth is to use a scale calibrated for Earth's gravity.
The scale shows 150 grams of mass.
Thanks. Now let's try to weigh this ball here in space. It weighs... Let's try that again. It weighs... Excuse me a minute. I'll be right back.
Hey there, John. You having some trouble?
Yes, Marty. You know, back on Earth, this scale worked just fine. But here in space, it's not working. Look at it. How am I supposed to weigh it if it does this?
Beats me. If it weren't for these shoulder restraints, I'd float away too. And then I couldn't do my experiment.
And what is your experiment?
It concerns the cardiovascular system. You know, the heart, arteries, and veins. We know from previous experience that the cardiovascular system becomes weaker in microgravity. We call this deconditioning. Deconditioning may reduce the cardiovascular system's exercise capacity during spaceflight and immediately after landing. We're trying to measure the amount of deconditioning that occurs, and also to find out whether exercise will improve or worsen this condition. In the Space Lab mock-up on the ground, scientists devised a specific set of instructions for me to follow in flight. In order to gather the data we need, we have to perform the experiment on the ground, during the flight, and after we land. The instructions make sure the experiment is run the same way all 3 times. If I didn't follow these instructions, the scientists couldn't form accurate conclusions from the data.
Why do the experiment on the ground at all, Marty?
Well, John, because scientists must have what we call controls in order to perform any kind of experiment.
Controls, huh? That's the experiment without the variable, right?
Right. And since the variable in this experiment is microgravity...
Oh, then your control has to be on the ground.
Right again. Now, there's just one more thing to remember. You have to perform the experiment and the control experiment in exactly the same way. That means that everything you use to do the experiment must be exactly the same, except for the variable. For instance, the bike I ride in space is the same kind of bike I ride on the ground. A different one would change the results of the experiment.
How would it change the results?
I can answer that. Say we want to find out which tablet is more effervescent, brand X or brand Y. I take the first tablet and drop it in the water, and it fizzes. I take the other tablet and put it in the other beaker, and look at it go. Wow. Which tablet would you say is more effervescent?
Brand X.
Wrong.
Brand Y?
Wrong again. You see, I didn't do the experiment in the same way, so nothing's been tested. The experiment is invalid.
No, we saw you do it the exact same way.
Touch those beakers.
This one's hot, but the other one's cold.
You see, this is actually two different experiments. One done in hot water, the other one done in cold water. In science, we can't compare apples and oranges, so we can't use this experiment to conclude which tablet is better.
Okay, I think I get this. You have to follow the instructions exactly.
And you got to have control experiments.
And those two experiments were done the exact same, except the variables, so they can be compared.
But I still don't understand how that astronaut's going to weigh that ball in space.
I'm Rick Searfoss, the pilot on this mission, and right now I'm in a laboratory at the Johnson Space Center. This is where scientists might come up with an idea they want to test in space. Here they would form a hypothesis and plan an experiment that would test their hypothesis. First, they'd ask a question like, how does microgravity affect your sense of balance? Then they'd look at the existing data, develop a hypothesis, such as microgravity makes humans depend more on what their eyes tell them than what their balance system tells them. Then they'd come up with an experiment to test that hypothesis, like this rotating dome experiment. Dave, could you tell us a little bit about this experiment?
Sure, Rick. I look into this dome at the rotating colored dots. The hypothesis says if the body relies mostly on balance cues, then my body will feel stationary and I won't move. But if my body depends more on what my eyes see than what my balance system indicates, the rotating dots will make me feel like I'm moving. My body will then tend to move, since it's a natural thing to try to steady one's position when you feel like you're moving.
Let's find out. And it looks like the hypothesis was correct. Up here, Dave's body seems to rely more on visual cues than balance cues. But doing the experiment once isn't enough, so he'll continue to do it. And other crew members will do the experiment as well. We call this repeatability, and it ensures that we have enough data to form correct conclusions.
Okay, so you get a formal hypothesis, come up with an experiment to test the hypothesis, and do the experiment more than once.
I bet there's more.
There is. I'm Bill MacArthur, and right now I'm in a student lab much like yours. These students are performing chemistry experiments, and it looks like everyone here is taking safety seriously. The students are wearing their goggles, aprons, and some are using vent hoods to carry away harmful fumes. Safety equipment is important to us too. Sometimes we wear safety goggles just like you do in your lab. But we don't always have to wear safety goggles and other such gear when we have specially designed equipment like the General Purpose Workstation. The GPWS, as we call it, provides a shield between us and potentially harmful substances like fumes and toxic materials. It also provides a container for items that would simply float away if the GPWS weren't there, like water. And look at how well it works. For safety reasons, any fluid we spill has to be sopped up immediately. That's because on orbit, liquid doesn't fall to the floor. Up here, it could float around and short-circuit a piece of electrical equipment, so thoroughly cleaning the GPWS is a safety must. In fact, the whole lab has to be kept clean so small objects don't fly into a crew member's eyes or drift into the lungs. And sharp objects have to be disposed of properly.
So safety's important. Anything else?
Yeah, labeling.
Labeling?
Sure, you have to properly label and identify all samples you take, for scientific reasons and for safety reasons. There's no point in taking a sample if you don't know where it came from or when it was gathered. An unknown sample would invalidate your experiment.
Oh, all right. So labeling's important too.
Hi, I'm Shannon Lucid, and right now I'm in a biochemistry lab. In this lab, as well as in all labs, it is important to measure correctly. Microgravity causes us to measure things in slightly different ways than we do on the ground.
Tell me about it.
Here, we use a graduated cylinder to measure the volume of liquids.
But up here, we have to use a syringe to do the same thing. We have a different kind of problem when we try to weigh something. And that's because in a free fall orbit, we can't measure weight at all. We can only measure mass. You can only weigh something when you have a force acting on it, a force applied by an acceleration, such as the gravitational pull at the Earth's surface. This is a body mass measurement device, and it takes the place of the scale we normally use on Earth. The part that John is sitting in is spring-driven to oscillate a rock back and forth in one direction. How fast it oscillates is directly proportional to the mass of the crew member. The greater the mass, the more resistance it has to moving.
I think we're on to something.
Looks like he's finally going to finish his experiment.
But I need something smaller. What can I use?
How about a small mass measurement instrument? It works just like the body mass measurement instrument, only on smaller objects. Activating the SMMI spring device causes the ball to oscillate, but the ball's mass causes it to resist the oscillations. The number of oscillations are put into an equation, and we use this equation to calculate the ball's mass.
That's 150 grams in space. Now, what was it on Earth?
150 grams.
Exactly the same. So, I'm finally able to show that the mass of the ball on Earth doesn't change just because we're in space.
The important thing about science is to keep asking questions and keep looking for answers.
That means forming temporary answers or hypotheses to your questions and designing experiments to prove or disprove them.
It also means obeying rules and procedures, like following the experiment's instructions and taking proper safety precautions.
And you've got to measure things properly, on Earth and in space.
We hope you've enjoyed your field trip to space, and we wish you many successful adventures in science. Who knows, maybe you'll be one of the scientists in the laboratory on the space station.
But whatever lab you're in, remember to follow the rules and procedures.
Everyone does, even astronauts.
And us too.